Okay, so this is Dirk, and I'm sitting in front of one of my Linux computers, and I'm presently just checking my sound levels, and I see that my sound levels are acceptable because I don't want to produce a distorted voice, let's say because I raise my voice momentarily. What I wanted to broadcast about today is the fact that we can not only dream up integrated circuits in our heads, or any other type of circuits, why integrated circuits, we can actually simulate what those circuits would do using a computer and using open source software, no less. So the software that I'm going to demonstrate right now is called GSpice UI. In other words, it's the user interface for a software system called Spice, produced by GNU, the makers of open source Linux software. GSpice UI, as the name might suggest, is a graphical front end for circuit simulation. SPICE stands for Simulation Program with Integrated Circuit Emphasis. Now, I have a different project loaded right now from the one I want to demonstrate. I'm going to demonstrate a project that works out of the box. When you have the demos loaded for GSpice, GSpice UI. One of the projects that works out of the box is the project called filter-bp-2.sch. That's a bandpass filter, and .sch means that it's a recognized type of schematic file. So I'm opening this particular project. I expect to get no error messages, and I basically get a netlist. This netlist being a shortened text version of the circuit diagram that I just loaded. But of course, I'd like to be able to view that circuit diagram. So there's a little icon here which looks like an AND gate. It says Edit View a Schematic, and when I click on it, it shows me the circuit diagram that I'm about to simulate. So it has an input voltage and an output resistor, and I'm noticing that it has fairly small capacitor values of 47 picofarads. It has small inductor values of 100 nanohenries. So all of this suggests that it's an ultra-high frequency circuit, if not a microwave circuit. And it's a bandpass filter, and I would like to simulate what its behavior is by using alternating current as my input. So if I've got AC selected as my test setup, I mean I can check for a transient, in other words a pulse. I can check for a DC sweep. I can check for what happens when there's only temperature acting on the circuit, but I'm doing an AC sweep. And I'm going to modify the parameters a little bit considering what I just observed. So I'm going to say that my start frequency will be 100 megahertz. I mean 10 megahertz. That my finishing frequency will be 100 megahertz. And that my steps per decade will be 100. I have a fairly powerful computer. I can afford to produce 1,000 different sampling steps. And in the settings of this program, we get to choose which of our simulators we wish to use. There's GNU-CAP, where CAP stands for Circuit Analysis Package, and there's NGSpice, which I'm mainly focusing on, and I select NGSpice, which was already selected. Because I'm specifying that I want an input signal to generate output, I have to specify where to apply the input signal to. And there's only one real choice, and that's voltage in. The schematic is designed so that that's the only available input for my test voltages. And I would like to monitor what results on resistor output. The resistor output voltage, I can have the complex numbers treated in different ways that result from the output. I can have the magnitude in decibels, and I can simultaneously choose that I would like the phase position displayed. And so, since I've set up the parameters of my simulation, I simply tell it to do the simulation by clicking on the little gear wheel. So my NGSpice output panel now shows me in scientific notations that it's got a set of frequencies in the first column, that it's got output voltages in the second column, and that it's got phase positions in the third column. All of this is rather useless to me unless I can plot it graphically. So to plot it graphically, we have a little tool here that looks like a squiggly line, like a little oscilloscope signal. And when we click on it, we might find that we get a disappointing result in that we've got a panel on the right that's supposed to sort of emulate what an oscilloscope used to do. And we've got this other panel on the left, which seems to have buttons. And you see, one of the disadvantages to using open source software is the fact that we do not have ease of use. I can click on a button, and yet because even though I've clicked on it, nothing appears in the oscilloscope view. So what I'm going to do is I'm going to demonstrate the crucial step that frequently people leave out who describe how to use this program, which is to drag the button into the oscilloscope view so that I get a frequency plot. And I'm already seeing that the peak frequency response is off the scale of the frequency plot because it's too far to the right. So I'm just going to cancel this for a moment, and I'm going to change my parameters to go from 10 to 500 megahertz instead of from 10 to 100 megahertz. I'm going to run the simulation again. So now, if I plot the results, again, I have to remember that the crucial way to use the little viewer is to drag, to take the button that represents the value that I want to see and to drag it into the view, thereby giving me a slightly better framed frequency response in decibels and also the phase position. So we notice that at the ideal frequency, the phase shift is 0. But we also know that the phase shift could go from minus 2.979 to plus 2.996 in radians. They don't use degrees, they use radians. So again, as punishment for using open source software, it's a little bit more difficult to use this program. But the thing is, it's fun to work with once you figured it out. So the lowest value here in the frequency response is minus 34.24. That's in decibels. And for some reason, it's telling me that the highest value is 799 M. The M stands for thousandths. What it's telling me is that the peak frequency response goes above 0 slightly, and it goes all the way up to 1/10 plus decibels. It goes up beyond 0 decibels, which is unit gain, up to 0.7992 decibels. It's a bit hard to visualize what that is. That means it just overshoots unit gain slightly where these peaks are. So the thing is that while we have this software to play with, we don't necessarily need to build a circuit. We can construct a schematic of a circuit, and the schematic of our circuit can be edited using another graphical user interface called GSchem, or GSCHEM, which stands for Schematic Editor, again by the same group of programmers. And here is the circuit that we just simulated. So we have options as to how to use this, but sometimes the instruction manuals don't tell us quite enough on little details like having to drag a button into our oscilloscope view. Thank you very much. That was it for